是这样的，比如说你就按着这个，然后同时转着这个。
因为给强度是吧？
然后我不知道你干嘛用这个，你直接用人按这个拍人像。对，这样就可以了。这样然后一样的。我看你怎么这么多设置？
我不知道。
是这样闪光就关了，然后要同时按的，然后这样自动。
现在是有闪光。
自动。拍进来了。可以啊。想嘛，请教，请教。这个问题太不让那个，请我的司机们。
上面虚拟窗没开。
啊？
虚拟窗没开。
去掉那个。你看到这个？
那我现在怎么回那个？
回到哪？
就现在就拍了。
这个是啥？不管。
Dames en heren, commissie.
Mijnheer de kandidaat, you are confronted by a committee that was appointed by the Council of Deans and that is charged with the task of examining both your dissertation and the propositions submitted therewith. The discussion will start with Professor Yujie Zhou.
Meneer de kandidaat, I read your thesis with pleasure. I like these systems that you can even build with Lego. And so you think they're easy, you can understand what's going on, but when you think deeper about them, they're very complex. And so I have also various questions. The first question is regarding the analogy between electronic systems and mechanical systems. I think you say something about this on page 13. There is an analogy between electronic systems and the property that they are either insulator or conductor. Thinking, for instance, about topological insulators. Then on the other side, the mechanical topological systems that can be either rigid and floppy. And so my question is this analogy just a way of inspiration? So you get inspiration about mechanical systems from these electronic systems, or is there a deeper connection between these two types of systems?
Hopefully the opponents, thank you for your kind words and question. I think this analogy between the electronic system and the mechanical system has some deep connection, meaning that, say, you can write down, say, the Hamiltonian in a similar manner, so that you can see that topological modes that appear in both systems. And also, phenomenologically, you can see that certain prediction can be made for both systems, namely the boundary modes that is robust against, say, the defect or impurity. And that's it.
And so the boundary modes would be, in the case of electronic systems, conducting, and in the case of a mechanical system, floppy? Would that be the connection in that case?
Yes. The short answer,
yes.
It would be yes, but the analogy is somehow still different, because in mechanical system, say what is actually being conducted is not wave function, but just the mechanical motion itself. While in electronic system, it's the wave function, or the wave function of electrons.
Okay, thank you. My second question is about these topological invariants that you introduce. Especially it's explained on page 8-9 in these figures. So this is for the system of rotators, and you can assign an integer to each of these systems, either whether they are right or left leaning. And I understand this sort of, but I have the feeling, just an intuitive feeling, that it's a very complicated way of assigning an integer to the system, and I was just wondering whether there are simpler ways, or where this idea to assign in this way comes from, maybe from an analogy to electronic systems.
Hopefully opponents. So actually, the original idea of topological mechanics in this system, in that system, the definition of the topological invariant is even more complex than what I have interpreted here. So in that case, you need to calculate the determinant of a so-called rigidity matrix that connects that relates the motion, the degrees of freedom to the extension of the bonds. But then you calculate the winding number, because the determinant of the rigidity matrix is a complex number, and you calculate the winding number of that complex number around the origin.
Right.
And which is also what I did here, but here I just give a picture of, say, both the motion, namely delta theta in the figure 1.5 and the delta L. And you can see that there is a wave shift which takes place in figure 1.5
Yes.
and figure 1.6. And the difference of the phase shift, whether it's one wave or zero wave, is indicates the integer of the topological invariance.
So I see you tried already to make it as easy as possible to understand.
Or in other words, give a physical intuition,
Right.
a grasp to the system.
Then I feel I would love to discuss a little bit the proposition 8, because I started out as a theoretical polymer physicist, the connection between this work and the block picture in polymer physics. May I ask Paranym to
a unique zero-energy vibrational mode can be associated with each bond removed from an isostatic lattice, the same way as the known fact that a state of surface stress can be associated with an added bond. This unique zero mode is quasi-localized and can be phenomenologically described by a theory inspired by the blob theory in polymer physics.
Thank you. Can you expand a little bit on that?
So for isostatic lattice, if we remove a bond, there will be a localized or quasi-localized mode associated with that. But that mode has zero energy, which means that if we cut more bonds, they are all degenerate, and somehow the shape of the modes are mixed together. So it's hard to say, if you just calculate it numerically, whether one mode is uniquely associated with the bond removed. So there's a method that I used, that I take from the reference by Daniel Sussman, that say we can find a way to isolate each mode that is associated with that bond, and then say, because this zero mode is quasi-localized, which means it actually expands. It's localized as a 1/r, as a power law decay, but not expansionary decay. So which is why it's quasi-localized. And so any given two zero modes will somehow feel each other in this way, and then the way they feel each other, it's like they are repelling each other, somehow like a blob. And the area that the area that each mode effectively cover is just the blob size. And the size of this unique mode determines its a quantity called inverse participation ratio, which characterizes how much localized mode is. So if we cut more and more bonds in the system, we can see that there are more and more blobs, and they are repelling each other, so that each blob is getting smaller and smaller, so that the inverse participation ratio becomes smaller.
Yes, I can see the analogy. Thank you.
Yes.
Manager Director, is still time for a question?
No, I think maybe in a second round. So
Good.
we continue now and
Thank
maybe later. So the discussion will be continued now by Dr. Giomi.
Yeah. So Meneer de Kandidaat, my first question has to do with your proposition number 2.
Yeah. The Maxwell-Calendine formula works for static frameworks. Extrapolating this formula to systems with finite mechanical energy can cause confusion, which can be solved by taking the perspective of the dynamical systems.
Indeed, so the confusion part is truthful, because indeed I felt a bit confused by reading this statement, and that's because somehow if you have a finite mechanical energy that does not compromise stability, in my view. I mean, you can have a system that is stable, so it's static, it doesn't evolve, and yet has a finite mechanical energy. So can you elaborate on this sentence a little bit? What does it mean that introducing finite mechanical energy implies that you need to look at dynamical systems?
Hopefully, opponents, thank you for your question. So this part of the work actually confused me for a very long time, and me and my collaborators and I have been thinking about it for a very long time, and so let me put it in this way. So for a system that has so we should go back to the Maxwell-Callendine formula. So when you have an isostatic system and you change the parameter, say in chapter 3, you change the length of a spring, and because it's isostatic or close to isostatic, you have a balance between the number of zero modes and the number of stiff cell stress. But at some point, when the parameter of that, the changing parameter, reaches a certain point, it drastically increase both the number of degrees freedom, the number of zero modes, and number of state of cell stress, which is somehow not physical, because there's a sharp jump, just because a changing of infinitesimal parameter. But to understand that, we need to turn to the dynamical system's perspective, meaning that given a finite energy, the definition of zero energy mode and state of cell stress becomes vague or becomes invalid, because those are defined for static system. But still, the zero mode manifests itself as some finite energy movement, which is like the trajectory, say in figure 3.7. So in figure 3.7, you can see that, say, when in subfigure A, you have it's a 2 degrees. You have a system with 2 degrees freedom, but effectively, the system is moving around the valley, which has 1 degree freedom, and while the other is oscillating around. Then you increase the energy. At some point, both degrees freedom becomes somehow free, and you can see that it's the system is meandering around the 2D plane, and somehow this system has indeed a true 2 degrees freedom. And so if you take finite energy, you can immediately see that it's just when your energy level, when the energy of the system reaches above a certain level, that both degrees freedom become free. And this somehow help to solve the drastic jump in a static system.
Okay. So another question that I have has to do with the kink propagation that you described in chapter 2 and 3. And so here you have this mechanical chain, you have a kink, and this kink is able to somehow move from one side to the other. And that reminds me a little bit what happens if you have, say, an Ising model, an Ising chain, so in one dimension, in which the spins at the two ends have been prepared to be anti-parallel. So one is up and one is down. Okay? And so inevitably the lowest energy configuration contains a domain wall, and this domain wall can move around with no energy cost. I know that this is not what happens in your system, because otherwise there would not be any surprise to some extent, right? So can you explain me what is the difference?
Hopefully opponents, thank you for your question. So there's indeed quite a similarity between these two systems, but I would say this is also my opinion about Ising model, is that it is not mechanical, meaning that there is no kinetic energy associated with that. So actually the kink can propagate, but it's just a flip of the spin at the boundary, which is the Hamiltonian itself doesn't tell you the dynamics of that process. I mean, it's just a flip. But well, for in the system here with the mechanical model, we have indeed a kinetic energy term, and so which enable us to write down a nonlinear equation and gives a profile of the 5-4 kink.
Okay. And so the fact that you mentioned kinetic energy makes me think about another question that I thought, which is the following. So, in all the equations that you present here, they are all second order in the time derivatives. I mean, you need, indeed, you need the mass, you need inertia, and this inertia is fundamental for wave propagations and so on. Nevertheless, there are a lot of systems, especially in soft matter, that are overdamped in the sense that inertia is, if not is very small. If not zero, is very small. Let's say it can always be neglected. Nevertheless, many of these systems, again in soft matter, typically contains more degrees of freedom. So density is one, but then, the simplest one is like position and orientation, for instance, and you can imagine things that are more complex. And so I was wondering if all these beautiful topological phenomena, which have something to do with waves, somehow do survive when you have no inertia.
Hopefully opponents, thank you for your question. This is a question that I have considered before, but do not have a good answer for that. I'm aware of there are some papers for calculating the topological modes for the jamming system, in which they also have dissipation terms. But I think to the first order, in the elastic mechanical system, I think the phenomenon will remain. But also if we take also the viscous system or in liquid system, I think there is also work in our group that shows that there can be topological modes that obviously exist in the sound propagation system.
Do we have more time? Or?
Maybe I'll keep you in mind for a second round too.
Okay.
And the discussion will be continued now by Dr. Frujaar.
Mijn geachte kandidaat, first let me thank you for your beautiful thesis, which was I enjoyed to read. My first question is about your chapters 2 and 3, where you have solitons propagating in one-dimensional chains. So if I understand correctly, in this mechanical system, there is a duality between zero modes, where you have free motion without bond elongation, and self-stress modes, where you have bond tensions without forces on the masses. And if I understand correctly, the soliton, the kink, is essentially the finite version of the zero mode. Am I correct in saying that the anti-kink is related to the self-stress mode?
Sehr geehrte opponents, thank you for your question. It is valid to say that the anti-kink is associated with the state of self-stress. And indeed, if there's a way, if you can say plot the bound stress with the spatial coordinates of the rotors, you can see there's also a bump or soliton-like shape in the middle. However, I should also say that it's not exactly, there's a not exact correspondence, because a state of self-stress exists for a system at where there's no pre-stress. Well, for anti-kink in the system, there's already a stress in there, which somehow there's still a way for us to calculate that, but the definition of state of self-stress does not exactly apply here.
I see. So the second question I have on this subject is, in this system where you have masses connected by harmonic bonds, it is not. I don't see a way, at least, to actuate or to activate the self-stress mode, even at the linear level, because it, I think, require to have a nonlinear bond, like a non-Hookean spring or something like that. If we add a degree of freedom to the bond, to be able, like for example, changing its equilibrium length, to be able to have, well, with this new degree of freedom to actuate the self-stress mode, would this change the behavior of the anti-kink? For example, would it propagate in the new degrees of freedom?
Sehr geehrte opponents, thanks for the question. So, for sure, adding a degrees freedom to control the length of the springs will say indeed change the system's property. And as you said, for a system in and of itself, it cannot be activated. The spring tensions cannot be activated as a free motion. So I'm not now aware of any methods that we can actually do that.
I see.
But still, I know that, say, for a normal 5-4 kink, just in the continuum theory, that kinks and anti-kinks behave the same. It's just like, say, or even not even continuous, but in normal 5-4 theory, where, say, Frank control model, where you also have kinks and anti-kinks in both systems, and there's a way to control both kink and anti-kinks motion.
But in this electronic system, is there the same duality than in mechanical systems?
Oh.
Like between zero modes and self-stress modes?
So in the electronic system, the zero mode just corresponds to the I think the energy, the currents of the electrons. But for the anti-kink, I think it also exists in the SSH model.
Yeah.
You can have both kink and anti-kink.
Mm-hmm.
But I believe that both can propagate and be controlled.
I see. Thanks. My second question is also about solitons, but more on figure 3.7. Well, this is kind of not an random question, but it reminds me of a billiard where you have balls rolling on the table, and I wonder first, is it possible to have like collisions between solitons in this kind of systems? And if so, would it be possible to create the analog of a billiard model in them? Maybe a chaotic billiard or something like that?
Ziegler opponent, thanks for the question. Yes, indeed, it is possible to have solitons interaction. However, here the system is what is so-called topological soliton, namely that when you have a kink, its neighbors must be anti-kinks. Otherwise, which is a restriction imposed by the topological boundary. So in other systems like KDV, where the soliton is not topological, then you can have you don't just have one type of soliton, and they just can freely interact with each other. So here, the only possible scenario for the soliton interaction is kink and anti-kink interaction.
Yes.
And yes, indeed, the way they interact the result can be multifold. They can, say, reflect each other, or they can merge into one, totally dissipates their energy and radiates into phonons. Or they can be, say, bonded together to become what is so-called intrinsic localized state, or also known as the breathing mode, which there's also a field of intense study on that.
Okay, thanks. Should I continue?
I think we should continue with the next opponent and may come back later. So the discussion will now be continued by Professor Beenakker.
Dank u wel, meneer de rector. Meneer de kandidaat. This is not my field, and so my questions will necessarily be a little bit on details. You know, it's like if you're not a professional art critic and you look at a painting, you don't see the big picture, but you zoom in on how did this painter, draw the details, and so I apologize for that already. Let's go to page 63. There are some differential equations there, which I think I understand. At least I've seen similar differential equations before. And there's an equation 4.7. And then you define something which you call D. You do this by multiplying both sides of that equation with the inverse of the matrix M. So the matrix M goes away on the left-hand side. And on the right-hand side, I then find minus M to the power minus 1, second derivative of phi, and that's what you call D. Right? So we're on the same page there. Then you do something else. U with the two dots is a double time derivative. And then you go to, I think you actually say this, you take a time Fourier transform, and then the double time derivative becomes omega squared. That's equation 4.8. Now, it's been a while since I did these things, but I think there's this thing that double time derivatives become, each time derivative is I times omega, and so double time derivative should become I squared times omega squared, and I squared is minus 1. So I think equation 4.8 shouldn't have a minus 1. Which is actually kind of crucial because it tells you whether something explodes or something damps. It's not just some silly minus sign. It changes the whole dynamics of the stability of the equation.
Hopefully, opponent, thanks for the question. I can clearly see your points, and I believe either that there's a typo here that I added where I define D with an actual minus sign in front. Here. Or where I made another typo in equation 4.7, because there should be only one, otherwise 2 minus m would be.
Typo. No, I mean if it's typo, there's no point in discussing it in much more detail. So then let's continue to the next page, which is a different question. Don't worry, I'm not going to just go from one typo to the next typo. This is footnote 1. In footnote 1, you use a term which is pseudo-Hermitian. I know what Hermitian is. I just do not know what pseudo-Hermitian is. So perhaps you can explain to me what is pseudo-Hermitian.
So, pseudo-Hermitian is a matrix which is pseudo-Hermitian is that it is not Hermitian by itself, but if you sandwich it by say 2 other matrices, and the results matrix becomes Hermitian, and
so we're talking about the matrix D, right?
Mm-hmm.
So could you tell me just as by speak out the formula which says sandwich? I don't know what's. So we have D, and then sandwich is, and then comes something.
You sandwich it the D by the matrix of the eigenvectors.
Are you referring to unitary transformation? I mean, I know unitary transformation is U, D, U dagger. Is that what you call sandwich?
But it's not that. It's like that. It's let me think about it. It's been a long time, but I believe that maybe I just said something wrong. It's that you take this think about it. I think the definition, I can't remember it in detail, but
that's okay.
it's more like you take the square roots, or it's like you're taking the transformation of something similar, like a sandwich, but the result, the right hand side, after taking the transformation, the result is also not just a matrix, but also can be written as a form of sandwiched thing.
Okay. I mean, there's no point in somehow trying to. I could look it up on the internet or whatever. But let's. I have one more. I think I just have time for one more question, if I'm not mistaken. This is my last question. So this is page 70. So let's see. The next to last paragraph, it says, we also investigate the eigenvectors, epsilon, special phenomenon, all eigenvectors equal mode amplitude, meaning the norm of the vector EIX, EI, epsilon IX, epsilon IJ is identical for I is 1, 2, 3. Now, as far as I understand, I, 1, 2, 3 labels eigenvalues, I presume, and then X and Y is coordinates. And here's what worries me. We're talking about eigenvectors. I thought eigenvectors were defined up to a normalization. So I don't know what it means to say that the norm of two eigenvectors is the same, because I can always multiply an eigenvector by some constant, non-zero constant, and it's still an eigenvector. So how can you compare the norm of two eigenvectors if you can multiply them by an arbitrary constant?
Holy opponents, thanks for the question. So actually, here it's not the eigenvector, but just which the eigenvector has 6 components.
Mm-hmm.
But here, the vector here has only 2 components. So it is like a subvector of the eigenvector, which is just like if you draw a vector just in the real space, you can see that it is just the direction.
But if I can multiply the vector by a constant, then I can also multiply the subvector by a constant. So how does that help? And a vector has 6 components, multiply all 6 components by a constant, then also the sub things will be multiplied by a constant.
But here, the point, what I wrote here is that each subvector itself, they have identical norm, which is not guaranteed.
Okay, so I is 1, 2, 3 does not label different,
but different particles.
But it does not. Okay, this is one single eigenvector.
Yes.
You're talking about. So I is 1, 2, 3 does not identify different.
No, it's identified for the 3 masses.
Oh, okay. So these are just. It's one vector of length 6, and I have 3.
Yes.
Okay, very good. I'm satisfied. Thank you very much.
Thank you. Then the discussion will be continued by Professor Eliel.
Meneer de kandidaat, you've given us a nice book to read with interesting physics. It's very stimulating, also as an experimental physicist and as a parent of children, to see how Lego can be stimulating modern research. It is gives me the feeling that even at home I can do things that were not discovered 15 years ago. And that's really something that's very important to realize, that you don't have to go to outer space or something like that to see something new, but that it's actually in front of your eyes if only you know how to look. And that's what I love about your thesis. I'm not an equation specialist as an experimental physicist, but I started, of course, to read, and you start with chapter 1. And I encountered the first 2 equations, 1.1 and 1.2. There's nothing wrong with the equations, but you suggest there's 2 equations, one about the angle of the individual rotor and the other about the length of the connecting spring. And it's in the text is kind of suggestive as if these are totally independent, as if you could have a delta theta mode which has no delta L associated with that. And I've not seen any of those in your thesis, but I also was wondering whether that's at all possible, just from a mechanical point of view.
Holy opponents, I now have some, I don't quite understand, but maybe I can rephrase. You mean that, say, delta L and delta theta are not the form of...
No, let me just say, is there a mode which has non-zero value for delta theta, but has absolutely uniform value 0 for delta L? So the things, you know, a meaningful wave, so different rotors are rotated by different amounts, but the springs are not lengthened in any way. I find it difficult, conceptually difficult to imagine. So. Because you say the normal modes as if they are independent, and it's just to be as if they are independent, but
so they are. I think the answer is they are not independent.
That's good. Okay, then maybe we move on to figure 1.3a. Where you show how the real and imaginary part of the function phi, the phase difference between those 2 parameters change, and in 1.3a you see that in that case of right-leaning rotors, the angle phi spans an arc. And that arc has an opening angle. And I was just wondering whether there's any physics in the opening angle, whether you looked at it. You know, if I make a different set of connectors, do I get a different opening angle, or is this value uniform, and does that mean something then?
So, hopefully, opponents, thanks for the question. So the opening angle can be seen physically or visually on page 8, figure 1.5 and 1.6, where the opening angle, I think it should be on 1.5 actually.
Yeah.
You see that, say, in the red curves on the right side, that the thickened one period of wave shifts. The center of it shifts back and forth from the origin.
Yeah.
And finally it reaches origin at, say, at the top. So this amount of shift just corresponds to the amount of opening angle.
No, I understand that, but you know, is there, you know, the amount of shift of these curves in figure 1.5 right side, is that you know, you suggest in the figure that that's limited, and that limit of shifts, is that somehow related to physics? And if so, what physics? But you may not have looked at that, and that's fine, but then we can move on to another point.
So I think it's I'm not aware of now that there's any physics related except for the cell phase.
Okay, good enough. Then let me move on to chapter 5, where you talk about a pair of defects in the Kagome lattice. And that's kind of interesting because you know, there's impurities are often a source of a lot of physics, and pairs of impurities can also be the source of a lot of rich physics, which, for instance, the nitrogen vacancy that plays an important role in quantum networks is exactly a pair of defects, one associated with a nitrogen atom and one with a lacking electron. So that piqued my interest, and then I looked at your, say, figure 5.7, where you show how the energy, so to say, of the impurity modes shifts when you bring those modes, those impurities, closer together. And lo and behold, what you get is originally they degenerate, especially in your case, they're simply, you know, missing or a weakened link, and so they must be degenerate. And then when they come to close together, what you expect, anybody who has done two-level systems, is that they will you get a new set of modes, and one has a lower energy, a binding orbital, you would call that in chemistry, and the other an anti-binding orbital. So there's level repulsion, we say in quantum mechanics. And so basically figure 5.8 does not really surprise me that one mode goes up and one mode goes down. And so what are you trying to tell me there? Is that the fact that these different approaches have roughly the same, give roughly the same result, or?
So in this figure, one, it's from direct diagonalization of the dynamic matrix, which somehow is the precise result.
Okay.
Well, omega TB is
Men, heer de kandidaat. The time allotted to the examination of your dissertation and its propositions has passed. The committee withdraws in order to deliberate. and I request that you and your company await our return here.
He contributed to that problem. So I vaguely remember that. But I asked him again after planning something like that.
Something you dagger because it would kill you. Because it doesn't change the car machine. So we should kill this time. I didn't understand what it was. Sorry, I didn't understand what it was.
Actually, I don't. I understand. It's not a. It's not published. It's not even. The work hasn't been done. It's open conversation.
It's nice if you can find
My supervisor is in camp, and who will be here if, at my defense.
I think promoter should also be there.
So both.
Yeah, that should be there.
Meneer de kandidaat, dames en heren, commissie.
Meneer de kandidaat, we have examined your dissertation and the propositions appended thereto. We have heard your defense and we have considered the report by the faculty concerning your previous studies. On the basis of this, we have decided to admit you to the doctorate. Professor Vitelli is empowered to confer that dignity upon you in the customary fashion.
Volgende aanvaardt hij de taak mij door de rector magnifique der universiteit opgedragen. Uiteraard dan van de bevoegdheid ons bij wet toegekend, volgens het besluit van de commissie, hier tegenwoordig verklaar ik bij deze u, Yujie Zhou, te behoren tot dokter. Ten bewijze hiervan zal u het diploma, de rector, secretaris en promotor ondertekenen en met het grote zegel de universiteit bevestigen, ter hand worden gesteld. Having completed the duty assigned to me, I may be the first to address you as doctor and to congratulate you on the award of the dignity you have obtained. This honorable distinction is a well-deserved and highly valued privilege. At the same time, you called upon never to lose sight of the obligation it imposes on you in the name of science and society. Dear Yujie, it's been a long way you've gone since the first Skype conversation we had when you were still a master student in China. I remember it being a difficult Skype conversation, partly because Skype doesn't always work that well with China, and partly because at the time we were still a bit timid about communicating in English about science, and I think that shyness has been gone, and you communicate very effectively in English today. And of course you learned also some physics in the process, which is always a good thing, especially because you went from a chemistry background in your undergraduate to continuing with a PhD in physics, which is an admirable effort. One of the key features of your personality is a certain carefulness, a desire to think for a long time and deeply about things before acting. I consider this feature a skill and a very valued attribute that you have. My last words as a PhD advisor concern the relationship between thinking and acting. Thinking is not a substitute for action, it's a complement for action. And I want to encourage you in your future to focus on the action part. And focusing on the action part requires two things. First of all, an ability to draw the line and to accept an outcome that could be imperfect as what has to be the things that have to be completed. To draw a line, not to continue with perfectionistic instinct. And the second thing is self-discipline, which is the ability to continue to put enormous attention, even when the fun parts, the creative parts have gone. What one has to do is to just persist and bring things to completion. I've seen some evidence of that already in the last stages of your PhD thesis, and I think you'll be very successful in life and in academia if you insist even more on these two aspects. Good luck.
Thank you. It is an agreeable duty for me, very learned sir, to congratulate you upon your degree, also on behalf of Leiden University and its Council of Deans. And herewith I declare this ceremony closed.